Welcome to the fastest way to learn data structures and algorithms with this premium revision material. Today we are mastering LeetCode 133, the Clone Graph Challenge. This is a fundamental graph problem, a cornerstone for understanding deep copies in graph traversals. Let us look at the problem statement. Given a reference of a node in a connected undirected graph, our task is to return a deep copy, or a clone, of the entire graph. Each node contains a value and a list of its neighbors. We cannot just copy the reference, every single node must be a brand new object in memory, with the exact same connection structure. Think of it like the Starship Transporter from a sci-fi movie. We are teleporting a complex network of space stations to a new galaxy. To ensure we do not create duplicate stations or get stuck in a teleportation loop, we keep a transport log. This log maps every original station to its new replica. If we see a station already in the log, we just use the replica. If not, we build a new one and record it. Our strategy is simple. We will use a hash map to store the mapping from original nodes to clone nodes. We can traverse the graph using either breadth-first search or depth-first search. For this walkthrough, we will use a BFS approach with a queue. Let us dive into the dry run. Look at the screen. We have our original graph on the left, and our empty clone map and queue on the right. We start at node 1. First, we create a clone of node 1. Let us call it prime 1. And add this pair to our clone map. Then, we push original node 1 into our queue. Now, we pop node 1 from the queue. We look at its neighbors. Node 2 and node 4. For node 2. It is not in our map yet. So, we create clone 2. Add it to the map, and link it as a neighbor to prime 1. We also push node 2 to the queue. Next. Node 4. Not in the map. We create clone 4. Map it, link it to prime 1. And push node 4 to the queue. Moving to the next step. We pop node 2. Its neighbors are 1 and 3. Node 1 is already in our map. So, we simply link clone 2 to the existing prime 1. Node 3 is new. We create clone 3. Map it, link it to clone 2. And push node 3 to the queue. We continue this process, linking neighbors and creating new clones only when necessary, until our queue is empty. By the end, our clone map has successfully rebuilt the entire graph structure in a new memory space. Now, let us look at the Python code. We start by handling the edge case. If the node is null, we return null. We initialize our Oltonu hash map, and our queue with the first node. We clone the first node and store it in the map immediately. Inside the while loop, we pop the current node, and iterate through its neighbors. For each neighbor, if it is not in the map, we create the clone and add it to the queue. Finally, we append the neighbor's clone to the current node's clone list. Looking at the complexity, the time complexity is O of v plus e, where v is the number of vertices and e is the number of edges, because we visit every node and every edge once. The space complexity is O of v, for the hash map storing the clones. And that is the Clone Graph Challenge, mastered. Save this video for your next technical interview, and follow Leo Academy for more such premium DSA guides.